All of them are included as open source and may be used by training models with your data. Spark NLP is an open source natural language processing library, built on top of Apache Spark and Spark ML. This article is a walkthrough of solving a realistic use case of natural language understanding in healthcare using Spark NLP Deep Learning Named Entity Recognition, DL-NER. It provides an easy API to integrate with ML pipelines. It is commercially supported by John Snow Labs. Spark NLP's annotators utilize rule-based algorithms, machine learning and some of them TensorFlow running under the hood to power specific deep learning implementations. The library covers many common NLP tasks, including tokenization, stemming, lemmatization, part-of-speech tagging, sentiment analysis, spell checking, named entity recognition, and more. The full list of annotators, pipelines and concepts is described in the online reference. It also provides pre-trained models, although they serve as a way of getting a feeling on how the library works, and not for production use. As a native extension of the Spark ML API, the library offers the capability to train, customize and save models so they can run on a cluster, other machines or saved for later. It is also easy to extend and customize models and pipelines, as we'll do here. This article focuses on a DL-NER annotator that will extract healthcare problems from a corpus of clinical notes in PDF format. Spark is an open source, Apache licensed, analytics engine and library for large-scale computation. By learning its API, users can easily produce programs that automatically run in distributed computing environments through the concept of RDD, which stands for Resilient Distributed Datasets. Over time, Spark has grown room for data scientists and have implemented the Data Frame API, which allows the users not having to learn anything about the underlying RDDs, and focus on data as schema-based tables. The power of Spark is that it allows storing these datasets in distributed memory, hence making it very fast for recurring algorithms that access the data repeatedly. Taking advantage of Spark jumps in when having a distributed storage, large enough data and algorithms that can be run in parallel to even the load. Another cool thing is, Spark has API for Java, Python and R aside from Scala, which is the main language. Spark has a module called Spark ML which introduces several machine learning components. Estimators, which are trainable algorithms, and transformers which are either a result of training an estimator, or an algorithm that doesn't require training at all. Both estimators and transformers can be part of a pipeline, which is no more and no less than a sequence of steps that execute in order, and are probably depending on each other's result. Spark NLP introduces NLP annotators that merge within this framework and its algorithms are meant to predict in parallel. The notebooks presented below are written both in Scala and Python, as a way of showing the library works in both languages. In this visualization, you can see the general flow of annotators and annotations in Spark NLP. As part of the pipeline you can have various annotators which are of a different nature, such as a part-of-speech or a tokenizer. It is also possible to train the complete model on TensorFlow, in Python, and convert it to a Spark NLP annotator model equivalent. Working with text is not always convenient when we desire to find relationships between characters and words. Hence, word embeddings are a key entry point for the understanding of text in context. They are fundamental to measure word similarity and distance at a mathematical view, and it allows us to compute relationships of their vector representation in space. Spark NLP includes a unique capability of distributing word embeddings sufficiently and automatically within a distributed Spark cluster. Being the latter an internal serialized form of the embeddings in order to take the most out of it when working in cluster mode. The library will make sure the workers on different nodes are able to reach such resources. As you can see, a pipeline takes as stages each one of our annotators in the right order. Notice we are calling fit, which is Spark ML's training function, but we are passing an empty data frame with a column called text to comply with document assemblers and general pipeline requirements. NER model is the result of a training process, originated by NER approach Spark ML estimator. This estimator is a TensorFlow DL model. There are two ways of loading TensorFlow models into Spark NLP, utilizing pre-generated graphs or Python reader which reads TensorFlow models into NER model. Utilizing Spark NLP's pre-generated graphs, we can train directly from the library, utilizing a familiar API as follows. As you can see, the pipeline interface is the same. If we were fitting this scenario, we would also fit on an empty dataset, since such training is coming from external dataset, files that are outside the pipeline. NER models in Spark NLP, as of today, can be only trained on CoINLL format, which looks like this. Basically, sentence-bounded rows with a token per row and its associated label on the fourth column, labeled as IOP format. We generated CoINLL dataset by using Spark NLP's tokenizer, in order to make sure we follow the same standard. Our NER model follows a BY-LSTM with convolutional neural networks scheme, utilizing word embeddings for token and subtoken analysis, in this case, 100 dimensions, but we usually end up running with 200 dimensions which yielded better results. We put this information into a class called NER model and then add the appropriate layers, for which the full implementation does not fit here. We use allow_soft_placement TensorFlow config option to continue anyway if a GPU device is not available. To use GPU, it may be required to include additional dependencies into the Spark NLP build. Let's dig deeper by adding a finisher annotator, and transforming only our desired annotator's output. Light pipelines are Spark NLP specific pipelines, equivalent to Spark ML pipeline, but meant to deal with smaller amounts of data. They're useful working with small datasets, debugging results, or when running either training or prediction from an API that serves one-off requests.